so it's nothing like half an hour happens here.
So, do you have any question?
Oh no, I'm just curious to have the questions. Actually, I have hard time even understanding.
This exercise sheet was very easy. No,
yeah.
It was quite dense.
Look, actually, problem with me is that I'm a very slow reader. So I have already took the books with P.Guillon, but I haven't yet
read all of them. You haven't read the 5 of them completely?
No, I haven't.
I'm very surprised.
Well, actually, I haven't yet started. Because I have, first I think I should go into the lections and then do it somehow. And well, some other stuff happens and you can concentrate and all that. Well, what matters to me is that I enjoy listening to the lections. Well, I got some foundations, so later, maybe several years later, I will be able to come back and read, and on this foundation I can build further.
Yes, it's always like this. It's good to keep attending things that one understands only half, because you're like accumulating some knowledge, even because this course is a Master 2 course, and it's not it's not very easy.
No, I think
it's normal that if you have this particular curriculum, maybe you.
I'm just very bad with remembering, memorizing definitions. Yeah, that's a problem, but well, so when I come to some comprehensive stuff, easy comprehend it. Something like Turing machine or cellular automaton, I have feelings already. But when I have memorized what entropy is and how I should come to full subshift or minimal subshift, I have hard time memorizing.
When you have problems with definitions, a good thing is, because in my course we don't have so much time, and I do some formal statements sometimes without giving many examples. So a good thing when you read the course is next to each definition to draw an example, to write an example next to it. If you don't fully understand, maybe you can help with the books.
That is why it takes so many times.
Yes, it takes time, but it's really worth it, because I think then you can have a...
Well, for now I kind of stuff everything inside my head, and later it will come. It does it by itself, actually. I get lots of knowledge, then a couple of years later I don't understand it. Something like this. I'm already used to this.
That's nice. That's a good point. So maybe...
So I think someone else should have a question.
Someone else has a question? Maybe while waiting for other people to arrive progressively, we can start like with go to an easy exercise. So I think so. You talked about minimality. Maybe we can quickly go through this minimality exercise. So minimality for subshift means that so a subshift is a set of by infinite words, or infinite words. Here it's in A to the n, and which is defined by forbidding some patterns. And the minimal subshift is a subshift where you cannot forbid one more pattern, otherwise it empties completely the set. You understand? So for example,
so we only allow one pattern in our subshift.
Sorry?
So if we forbid one more pattern in the form empty, so we allow only one pattern. Like that?
No, because in some sense yes, but the minimal subshift is a set of infinite words, and you forbid finite patterns. For example, I forbid 1, 1, 1, and 0, 0, 0. And so, what is the set of configurations that are the same? Configuration and infinite words is the same.
Right.
Let's try to build one configuration which avoids these two patterns. So the alphabet is 0, 1. And we are looking at one-sided sequence. Okay? So let's try to build one. Okay, maybe we start with 0. Okay?
We can have 2 zeros.
We can have 2 zeros, okay?
And we can have 1, 0, 1, 0, 1.
1 zeros.
Yes, okay.
And any combination of well, 2 zeros and 0 next to 1.
1 0 and 1 0 0.
Yes. So, in some sense, I can write. I can write it like this. 0, 1, 0, 0. This. Infinite number, but then I have to say the orbit of this. Okay? It can start, this is the orbit of sigma, which means I take all the shifts of these sequences. This is a kind of clumsy writing, but you understand what it means. I have a choice each time I take this. Okay?
The power.
Yeah, so I think here today we are dealing only with one-sided sequences. And here, either, I don't know if you prefer, we can write this. But anyway, it's not a very formal writing. Okay? So, is this minimal? So see if it's minimal, we can okay. So if it's not minimal, it means you can forbid one word without emptying the set.
Yeah, we can forbid 2 zeros.
2 zeros, okay.
And we still have sets of 0, 1, 0, 1, 0, 1.
And it was not forbidden before, so we have a strict subsystem. And here you have, what is the set of configurations that you can obtain? 0, 1, 0, 1, 1, 0, 1, 0.
We can start with either with 0, 1, and we have them
and there is also
words. 0 next to 1, but it doesn't matter whether we start with 0 or with 1, because we have infinite words. If I understand.
So you have this one, and you have the shift of this one, which is the same, starting with a 0. Do you have something else?
I don't see anything else.
So is this minimal?
Well, according to definition, should be yes.
We can forbidden 0.
So if you forbid 1, 0, what happens? What happens?
Only once.
Only once, but
We can have two ones together.
you have to forbid one more word than was already forbidden. Then you keep these forbidden words, and then it gets empty. So, and every word that you want to forbid empties completely the set. So this is minimal. Okay? And it's not difficult to see that every periodic orbit is a minimal subshift. This could have been the first question of the exercise. And so, the full shift is minimal. The full shift is the set of all infinite words. Is it minimal?
Maybe only in case when alphabet is one letter.
Correct, yes. So if the alphabet has one letter, then it's just a periodic orbit. But if it has two or more, for example, you can even forbid one letter, and then you get a sub-alphabet with at least one configuration. But more generally, you can define many periodic orbits inside the full shift. You can define all periodic orbits on alphabet A, or included in the full shift. So you can define them by forbidding finite patterns. By the way, it's even a minimal subshift of finite types. This can be an exercise also, it's not difficult. So now I am given a subshift. Let's go more or less to question 3. I am given any subshift. Remember a characterization of subshifts, that it can be written XF for some space F of finite patterns. But maybe F is not finite. Patterns are finite, but set is not finite. Any subshift can be written like this. You remember what X index F means? It's the set of configurations that avoid all patterns in F. So we suppose that it's non-empty. Does it contain one minimal subshift?
There was something about containing at least one minimal subshift.
Why?
Well, if it's not empty, then we can expand it, and when it grows bigger, there is something that had one
Expand what? Expand?
subshift.
Expand the subshift?
No, well,
Expand the list of forbidden patterns.
yes. No. Otherwise, We have some list of forbidden patterns which can grow
Yes, yeah, I think.
lesser and lesser, and we will have more available patterns.
Yes. But for example, what we want is to find a minimal subshift inside XS.
So
we
we
want
should
less available
see
patterns.
if there is some set of forbidden patterns that would be maximum before it becomes empty.
Yes.
Uh,
So is XS minimal? Yes. So, well, it includes a minimal subshift because XS includes itself. No. Then it means, by what we have said, that there exists a word which is not forbidden.
Well, then we can forbid it, and it will be obvious sooner or later.
Why?
I don't know. I think it's obvious.
So it's obvious because the number here we can
We have finite number of words available. Finite patterns. We have finite alphabet, so we should have finite, even if big patterns of words. No?
finite or countable. You have a finite number of patterns of each length,
Yes.
and you can enumerate them. But the length grows, so you have infinitely many possible patterns. Maybe you need sometimes to forbid infinitely many patterns to get a minimal subshift. But it's countable, and you can enumerate, so you can describe your subshift by each time forbidding the smallest word, for example, that so maybe I can index this SI, and I can write SI plus 1 equals SI.
That I don't understand. If we have a minimal word, and we forbid every possible minimal word, so every word bigger than minimal will be forbidden too. Isn't that right? So we don't need to forbid long words, actually. We have, if our alphabet is finite.
So it depends. No, it depends. So what you're asking is, you're asking for a subshift which is not of finite type and which does not contain any subshift of finite type, any non-empty subshift of finite type. So do you know one?
If F is only 1, 1, and alphabet is 1, 0.
Yes?
And then we must describe where it was like 1 from 0 is 1.
Mm-hmm. Yes, but then this is a subshift of finite type, and it's not minimal. But can we find a subshift which is minimal, but which is not a subshift of finite type? Here we have examples of subshifts of finite type which are minimal.
Minimal but not of finite type.
And yes, and I think we saw in the lesson on finite type subshifts that the only subshifts of finite type which are minimal are the periodic orbits. Now, do we have other examples of minimal subshifts? We saw it in the following lesson with substitutive subshifts. For example, the subshift generated by the Fibonacci word Because I didn't go to the end because I don't have enough room on the blackboard.
They have
But
not periodic.
it's not periodic. But of course, I cannot convince you completely by just writing a finite.
No.
But at some point, you see, here the bunches of 0 sometimes are 1 and 2, okay? And the number of consecutive 2 bunches of 0 sometimes are 2 or 1, and the same at each scale. And to force this kind of scale, we have this definition by the substitution that we define. And this is a primitive substitution, so it gives a minimal subshift. And here it cannot be defined by a finite number of patterns, because we saw in the previous lesson that in SFT, if you're minimal, then you're periodic. Okay? So, but we didn't completely explicit all the forbidden patterns because there are infinitely many of them, so we cannot write all of them. But we wrote that they are exactly the set of patterns which do not appear inside the image by kappa of some letter. So it's the U such that for all T, U does not appear in kappa T of 0. In general, I put 0 or 1, any letter of the alphabet, but here it doesn't matter because 1 gives 0. In this particular case, it's this. The forbidden patterns are these ones. Okay? There are infinitely many of them, and you know that you cannot express this subshift with a finite number of patterns. So you see, because the intuition is, because you want to try to forbid more and more patterns, but of course you can always choose one which, but of course, you can convince yourself at home when trying on the paper, even without thinking about substitution, you forbid one word of length 2. Okay? Then you look at possible infinite words that you still allow, and you try to forbid one which has a small period. So you forbid a longer pattern to prevent your allowed configurations to have a small period. And then you forbid longer words to prevent some longer period. And by an infinite process, you will prevent all periodic words. You can convince that there is such a process, but of course, such a process is hard to explicit, except if you smartly use some kind of substitution, for example, and prove that there is minimality. Okay, but just to finish the first exercise, here if I take the intersection of all these subshifts, then it's a minimal subshift. Included in X0, which is because for example, we can take UI to have minimum length. UI to have minimum length among the words that are not in FI. So after a while, we will have forbidden so suppose that this is, so first we have to prove that it's a subshift, but it's an intersection of closed and shift invariant non-empty sets, which is decreasing by compactness. It's also non-empty and closed. And of course it's shift invariant. And if it was not minimal, then there would be a pattern that you can still forbid. But then this pattern should have been forbidden much before. Because if this intersection is strictly decreasing for every I, if it's not strictly decreasing, it means at some point I have reached minimal subshifts, so it's over. Otherwise, it's strictly decreasing, which means you have forbidden infinitely many words, so with unbounded length. But if this is a subshift which is not minimal, there is a finite word that I can forbid without making this empty, then I should have chosen this one at some moment before choosing longer words. So it's a contradiction. So it's kind of obvious, but you have to, yes, you have to first think about compactness, then think about this kind of minimality argument to have a contradiction, and it's in the general case, for example, this is true for dynamical systems, but in the general case, you need Zorn's lemma, so it's not completely obvious, because you have some kind of intersection of...
So in the end, we can theoretically have some long enough words which we can't make minimal, or not?
Yes. Be careful, I think you're using the word minimal in not in the same sense as I am using it. Minimal refers to the subshift,
yes,
which means I cannot have a small subshift in it without making this empty. Okay?
Yeah.
I think what you're saying is to try to take small words inside. When you forbid many words, you want to forbid the smallest possible word each time.
No, I'm referring to the right word. Just that I'm trying to kind of get final understanding about whether we can have that minimal subshift or we cannot then. Well, the question was whether we can have minimal subshift for every...
And the answer is yes, because we have built one.
Okay, the answer is yes.
So what we must do then, that f is equal to 1, 1 and alphabet is 0, 1.
As an example. Yes, as an example. So f is equal to 1, 1, for example, and
alphabet is 0, 1.
Alphabet is 0, 1. So, is it minimal? No. So, it means I can forbid, for example, I cannot forbid 0, because it will be empty, but I can forbid 1, the smallest length. I forbid 1, and then I get the only configuration is only zeros. So after one set is stabilized. just a little more complicated. You forbid this you start from this subshift. You cannot forbid 1, you cannot forbid 0. Because if you forbid any length 1 pattern, then you get empty subshift. Because you are really only in words like this. So you start with the length 2, and actually length 2 also. So I think in most examples, not in most examples, but if you start with an SFT at the beginning, if you start this with an SFT, then this will eventually occur in finite time that you have a set of minimal subshifts, because in every SFT you have a periodic orbit, and you will get to a periodic orbit. I think maybe I'm saying something wrong, but I think this method always reach a periodic orbit here if you start from an SFT. Okay. This sheet was very long. So maybe since I started talking about substitutions, we can also revise the things on substitution and go to exercise 6. So we have this substitution, and we are looking at the subshift, which is associated to this substitution. So we have to prove that it's aperiodic and minimal. Do you remember how maybe we need to draw something, an object associated to this substitution? What do you want to do when there is such a substitution? I think, what did we do with the Fibonacci substitution? Yes. So the matrix is 1, 1, 1, 1. And the graph is the full graph. So does it have some properties? This matrix, this graph? Okay, this is the idealization.
There are also the matrix N, what N times N is equal to identity matrix. Also, combination.
There is no such N. Yes? But even more than this, so when you look at this graph, what properties does it have? It's strongly connected, yes. And actually, it's even primitive. All coefficients are simultaneously non-zero, which means that it's strongly connected and that the greatest common divisor of the cycles is 1. So this is not enough to prove hyperrealisticity and minimality from the course. Maybe we can get convinced of this by also answering the following questions at the same time. Maybe they are easier for you. Is there a fixed point by this substitution? A fixed point is an infinite word, so that when I apply consecutively theta to each letter and concatenate them, I get the same thing. So for example, is there a fixed point starting with 0? 0, 1.
0, 1.
And then?
0, 1.
Here it is?
Yes.
So let's apply theta to this. Theta 0. 0, 1. Theta of 1. 1, 0. So it's different. But, okay, so this is not a fixed point. But if I have the first letter, I'm trying to find a fixed point starting with 0. What should be the second letter?
1.
1, yes, because we know that this 0, 1 should be 0, this 0 should be 0, 1, okay? What should be the third letter?
1.
Yes, you know that after this you have 1, 0 because it should be the image of this. Okay? So, if you want this to be equal to this, because you want a fixed point, then you also have 1, 0 and 0, 1. Okay? Actually, you can show that there is this big point, the orbit closure, is the subshift of the substitution. So, at least the first inclusion, if I have, so if it's minimal, then you know that the orbit closure of any configuration gives you a pole shift. So we have to prove that X is included in this, and then minimality will reflect the equality. Why is X included in the subshift? The subshift, the definition of the subshift is that every allowed pattern should be inside so I take any pattern here. Is it inside the iteration of one letter? Yes, actually.
0, 1.
Yes. Actually, this word X can be obtained as the limit of the iterations of theta over letter 0. If I write letter 0, that's what I did to write it actually. I write letter 0, this is theta of 0, theta 2 of 0 is 0, 1, 1, 0, theta 3 theta 4, etc. And you see that, you remember when I told you about this limit, this topology that you can also consider on the set of finite and infinite words. You imagine that you have a blank symbol here. Okay? So they are all infinite words. And there is a topology on A to the n, on A union the blank symbol to the n, which gives you directly a topology on the set of finite and infinite words. And in this topology, you can prove that this sequence of words converges to our fixed point. You define the topology if you want the formal version, but I think without the formal version, it's obvious to everyone what happens, that this converges. Okay? And this is true always when you have a letter whose image starts with itself and whose iterations of images grow to infinity, of course. So if you have 0 theta of 0 starts with 0, and the length of theta of 0 goes to infinity. If you have these two conditions, then theta t of 0 converges to some fixed point. And in particular, all the patterns which are in this fixed point are allowed in x theta. So x is in x theta because the finite patterns of x are all finite patterns allowed in x theta. And I don't know if you remember why x theta is minimal when the matrix is primitive. So minimal, another characterization of minimal is that for every pattern, I can find the size of a window in which this pattern appears everywhere. For every u in L of theta, there is this size of window, such that for all x in L theta, u appears in the prefix of length n of x. Actually, it appears in every factor of length n in every subword of length n of x. But this is equivalent because of shift invariance. Sorry, you should. This is x theta. Maybe I should call it y. Okay. So why do we have this property when the matrix is primitive?
Primitive means that everything m to the power of k is positive.
Mm-hmm. So essentially, you have the definition of u is in L of x theta. The definition is that there exists u.
That u is in the orbit of the planet.
Yes. Normally, I didn't really use the word orbit, but yes, you're right. We can also say orbit. A such that u appears in theta t of A. Okay. And so maybe we can remember that here theta of for all infinities means that for all there is t prime maybe or n such that for all b, a, b, and a appears in theta n of b. So in particular, if we put these two things together, u appears in theta n plus t of nb. But n and t are fixed. There exists n t, so there exists a power that just u appears in the So now, if you take the maximal, so this is n, so I shouldn't have called this n. Sorry, let's call it t prime. And we can say that there is this n which is equal to t plus t prime, such that this. No, sorry, it's not the same n. Again, let's keep it like this, but n will be the maximal length of the set t plus t prime of this. Then, or maybe twice this. Let's put it 2, maybe. I will see there if we need a 2. So, now for any y in x theta, y0 n is the L of x theta, so y0 n appears in some theta of, I missed indices, theta to the j of some letter C. Sorry. Now I understand what I did wrong. Excuse me. So n, we want n to be the minimal length which is bigger than every image of theta t plus t prime of v. I think it. I need you to help me. Let's see the final condition that we need. We need J to be greater the answer is very the conclusion is very simple. You just need to find the sufficient length so that you are sure to see one of these images here. What is it? Because I'm on the blackboard, I don't manage. So either I let you 2 minutes to think about this and I find the answer, maybe, or you find the answer.
Why?
I want n greater than the maximum of the A of theta prime of B 2 times this. And you see that J must be bigger than T plus T prime because n is very big, so it cannot be the image of a letter smaller than T plus T prime. And hence, you can write y0n plus some word here. So y0n appears in some longer words, which is exactly the image of subletter. And this image of subletter, I decompose the first steps, and I arrive with some text T plus T prime. And actually, this means that I can decompose my word here as a concatenation of images of letters by theta of T plus T prime. See, this word is an image of a word by theta T plus T prime, and since this is a monoid homomorphism, this is equal to the concatenation of images by theta T plus T prime of subletters of some word. But if you concatenate these letters, these words, these images of letters, since n, this length here, is bigger than twice the maximum size of these images, then there must be exactly, not exactly, but there must be one of these images which lies exactly, not exactly, which lies completely inside this pattern. Okay, and this is over because then you have some B such that theta T plus T prime of B is inside the word that we wanted, but also you know that U is in this for every B. So now we have what we wanted, that U appears. Okay? So essentially, yes, if you look at what happens in the fixed point, you understand more or less everything on the substitution. All the words that appear, so we proved first that all the words in the fixed point, this is not very difficult, they are in the subsheet, but actually all the words in the subsheet appear in the fixed point. And you see more or less why here, because since this matrix mixes in some sense, the letters. There is no isolated letter here which just goes to itself like this. It really mixes. So when I want a word which can be obtained by iterations of the substitutions, they appear here in this orbit of the substitution. Is it more or less, do you more or less get the intuition behind this? So a primitive substitution is minimal. Okay, after this I asked about the frequency. The frequency can be obtained by Perron-Frobenius eigenvalue and eigenvectors. We saw it briefly in some course. Yes, and this can be more or less understood on a fixed point because the length here, the growth of the length is given by an exponential with respect to the Perron-Frobenius eigenvalue of the matrix. And inside these words, the proportion of 0 and 1 is given by eigenvectors. But in that particular case, it's even simpler to get proportion 1 and 0. What do you think? The frequency of 1 and 0. For example, here.
Remains the same and
The same then. Yes, no, go on with your idea.
Symptotically, it must be the same.
Yes. Even not asymptotically, actually. Even
the
in the
difference is the initial letter.
Not in the initial multiplication.
Yes. But, yes, okay. Yes, you're right. But it's really, because the matrix is completely symmetric, you see that 0 and 1 play perfectly the same role. So if I change zeros to 1 and 1 to 0, I get actually the same subshift. So if the frequency exists, then they should be equal. This doesn't prove that they are, what I've just said doesn't prove that frequency exists, but you know that it exists by the theory here, by the Perron-Frobenius theory. Maybe we can. So it's a little more complicated to find the frequency of 0, 0. But to find the frequency of other words, you can find the frequency, you can look at where they happened by the definition of the language. So if I want the frequency of 0, 0, 0, 0 appears in the image of some letters. So it appears for example, you can see it here in the image of by theta 3 of 0.
Maybe we can just compute the iterations that reach occurs the needed word.
Yes.
And it will be the frequency.
So there is something to check whether the cases where you have because you will, if it happens here, you can look at all the third iterations for every letter, but then you also have to look at whether it happens on the boundary of two of them. And yes, and 0, 0, 0. What's the frequency of 0, 0, 0 in this word? And how many times does 0, 0, 0 appear? Here.
It doesn't appear.
It doesn't appear. You can easily prove that it's not in the language. So what's the frequency? Zero. Yeah. It's even better than frequency 0, or worse, I don't know. It's never really. Okay. Attack. Which we have 20 minutes left. Which exercise would you want to talk about? We can either continue to speak about frequencies, or we can speak a little about Sturmian. The second exercise is, maybe we won't spend 20 minutes on it, because I think you can really do it by yourself if you haven't yet done it. It's not difficult. And at the end we get to this result, this Morse-Hedlund theorem, that if you have one subshift with complexity n for some n, or bounded by n, then you know that your subshift is finite. It's a unitary configuration, for ultimately periodic configuration. And this motivates the definition of Sturmian subshifts as those with a complexity n plus 1. Okay, but in exercise 3, I kind of helped you quite a lot to prove that Sturmian subshifts can also be defined as balanced subshifts, which means that the number of 0 and of 1s in every finite pattern is nearly the same. Is it the case here? Is this a Sturmian subshift? For example, if I take patterns of length 2, here I have 2 1s, and here I have 0 1s. So it's not balanced, because balanced means that I can have a difference of at least 1. The Fibonacci subshift is balanced. If I take patterns of length 2, I never have 1 1. So I know that they are balanced. If I take patterns of length 3, I always see 1 or 2 1s. So it's balanced. It's balanced up to length 3. And if I take patterns of length 4, it's still true. I always see 2 1s or 1 1. Okay? But this one is not balanced. It's not a Sturmian. It's not a Sturmian subshift. And exercise 3 helps you to prove that balanced subshift is the same as having complexity n plus 1. And exercise 4 helps you to prove one of the two implications of the next equivalence, which is that Sturmian subshift can also be defined. You remember maybe in the first lecture when I drew these grids and told you that Sturmian subshifts can be obtained by looking at the intersection of an irrational line with the grid. So this is linked to this is what we're doing in exercise 4. Don't hesitate to do pictures if you need. In exercise 5, there are hints towards another characterization which I talked a little about in the last lecture, in the lecture of last week, which is that Sturmian subshift can be defined by iterations within a sequence of substitution. Do you want to go through one of these rapidly, or otherwise we can quickly go to exercise 7. No preference? Only 7? Okay. So 7 is like a kind of opening to algorithmic theory. I don't know if you know some things about this. So we are interested in the measures such that when I apply sigma, how do I write it? When I apply sigma to a measurable set, I don't change the measure. When I look at the measure of the pre-image, because in some sense, when you have a topological dynamical system, it induces some kind of dynamical system over the set of measures. So, I don't know if you read the whole sheet, but when I say measure, I always mean probability measure, which means that the measure of the whole space is 1. And for example, if I have a dynamical system where most of my points will so let's say that I have half of my point which goes to the second half, and the second half stays. I don't care about the exact dynamics, but all of these points I don't find them after one step. If I take a measure, a uniform measure, let's say I have a notion of uniform measure, I take some points randomly. After one step, you agree that I'm sure to be here. And so the system has changed the measure 1/2, 1/2 in some sense to the measure 0, 1. How is it formalized? We say that f of a measure is a new measure which maps every measurable set to the measure of the pre-image of this set. Do you understand why? We have a measure on the, maybe you can imagine, maybe it's better to imagine that f changes the space. So you have f from some space to another space, and you want to define what how f acts on measures. You have mu, a measure on x, and f of mu is a measure on y, which is defined by, how can I define a measure like this? I take the probability that I had before applying f to be in the pre-image of A. This corresponds exactly to the probability of being in A after applying A, after applying F. Sometimes it looks kind of weird to have this -1, but it's really this. The probability of being after applying F in A is the same as the probability of being in F -1 of A before applying F. Okay, so, but here we want measures which are not modified by the application of f, which means that f of mu is equal to mu. Okay? So, we want a Borel probability measure, so it has to give some it has to be defined on cylinders. Okay. this is defined. So it's defined on every open set. Yes, so let's go to question 1. So if you define phi of u to be u of the cylinder, what are the properties of the map phi? Phi of the empty word, we said that it's the probability of the whole space, so it's 1, because it's a probability measure. And phi of UA, sum for A in A of phi of UA, sorry.
By S of the space of words?
Yes.
Okay.
Alright. From A star. I'm solving question 1 here. It gives the probability to each word, which corresponds to the probability to the measure of the cylinder. Okay? And here, what can you say about this sum of phi of UA? Sum of phi of UA, by definition, is sum of these cylinders okay? But these cylinders are disjoint. So the sum of their measures is the measure of the union. What is the, what is the union of these cylinders?
Cylinder of fuel.
Yes, it's just the cylinder of fuels. If I take the set of configurations which have U, you remember that when I write cylinder U, it means cylinder U in position 0. Okay? Here we are in A to the N, so it's the prefixes. It's a set of configuration which starts by U. Set of configurations which have prefix U. And if I take the set of configurations which has prefix UA, and the set of configurations which has prefix UB, and the set of configurations which has prefix NU, and any other letter after this, I do the union. Of course, it's the set of configurations which have prefix U. So we have the two properties that were asked in question 1. Okay? Now, conversely, if you have a function phi which has these two properties, you can prove that it defines a measure, an invariant measure. Because the cylinders generate the whole topology. So, yes. They generate, of course, the sigma algebra. So it's not the same sigma. The sigma algebra is the set of unions and intersections of all cylinders, and in the end you get get all measurable sets this way. So if you define for any measurable set the measure by taking the prescribed measure on cylinders and taking additions and subtractions when you do unions and intersections, you get to what defines measure on the Borel set. Configuration X has frequencies for every pattern U show that phi induces a shift invariant measure on the shift generated by X. Okay, so we can use what we just said. If there is a frequency, maybe I can just define phi of U as the frequency of U. So, how is it defined? The limit, when n goes to infinity, of a number of occurrences less than n minus length of U. So if this limit exists, then we say we have a frequency, and I can define phi of U to be this. Phi of the empty word, what is it? Well, actually, all the i's are an occurrence of the empty word. So it's the width of n over n. The empty word occur as a subword everywhere. It's a bit stupid. Now, the frequency of UA, you can do the computation and you will find the other equality. I mean, I can do it, but it's really straightforward. Because when U occurs, of course, except if it's the suffix in position n, which is a specific case that you have to get out of this, but it's asymptotically very small. Except in that case, U is always followed by one letter, so you are always in one of these cases. So you have defined a phi which satisfies these conditions, and so you have a invariant measure. Such that the measure of each cylinder is the common frequency in all words.
Can you say this is a top definition of
frequency?
You. You can just say in words.
So you take all prefixes of x, you take any x. Sorry. Yes. Yes. No, it's this. You take all prefixes of length n x. The good thing with our assumption, you can take any x, because the frequency is
So for any x from...
yeah, no, okay, no, sorry, I forget about my last sentence, I was thinking about the next question. You take the x that we are asking, we want a shift in the measure on the shift generated by x. Okay? You take x, and we assume that there is a frequency. What does it mean? It means the frequency, this is the frequency. It means that you take all prefixes of length n of x, there is one. You take the prefix of length n of x, you count the number of times u appears, and you divide by the length, which is n, okay? And you take bigger and bigger prefixes, and having a frequency means that this sequence has a limit. It's really quite intuitive. You see, you're reading your word, and at each step you're reading this infinite word, for example, and at each step I'm asking you, what's the proportion of one you've seen? And if you're in a very strange word, maybe you will see, it's a 0.8, 0.2, and it can be always very, very different. If, for example, I'm writing 1 to the power n, then 0 to the power n squared, then 1 to the power n squared, 1 to the power n means n ones, then n squared zeros, then n cubed ones, then 0, n to the fourth zeros. This kind of word does not have frequency. If I ask you somewhere, what's the proportion of ones that you saw? Maybe it will be very, very big if you just after a bunch of ones, or very small if you're just after a bunch of zeros. It doesn't converge. But in some systems, which will be uniquely algebraic subshifts, then it exists. In Sturmian words, it exists. In primitive substitutive subshifts, it exists. In many interesting places, it exists. Okay, we have an inherent measure, and what I just said is that you can always define, if there is a frequency in x, you can always define one inherent measure on the subshift that it generates, which is defined by the frequency as the measure of the cylinder. Remember that this is the measure of u. Okay? And conversely, every invariant measure is built like this with a frequency if we are in this specific case of uniquely algebraic. Uniquely algebraic is a very interesting notion, which is when there is only one invariant measure. There is one invariant measure in the system, and then you have many properties. In particular, it's very used in theoretical physics because it means that you let your system evolve over one initial point, and you do some measurements in the orbit of this point, and you do an average of all the measurements that you do, and the temporal average of measurements that you do in this orbit, you know that it's relevant, it's equal to the spatial average, which means that you don't need, for physics it's very interesting because it means that you don't need to do measurements on many different positions randomly. You can just take one position and do the measurements on the same point, but by letting him follow the rule of the dynamic of system. It's a very strong notion of something that mixes. The orbit goes a bit everywhere and uniformly. Many systems in the real life are uniquely ergodic. You have, for example, you know that when you I don't know, a molecule of azote of nitrogen in the air, you can look where it goes when there is some wind, and you more or less have an idea of where all molecules go. If you just look at one, because you know that the system is not very specific, like having this molecule stand in some place. This is what unique ergodicity is about. And in subshift, it's translated by the fact that you have a frequency for all words, and the frequency is the same in every X in the subshift. But I don't solve formally for two reasons, because it's already 2 o'clock, and also because I gave you a hint in the third questions, which makes normally this question quite easy. Because if you assume the ergodic theorem, the Birkhoff, it's nearly straightforward to turn it into a notion of frequency. Are there any questions about this or about the other exercises that we didn't have time to correct? No? Everything is understood. That's how I interpret your question. Okay. So if you finish the sheet at home and you have questions, don't hesitate to come with questions. You can even, if there are important questions that really you get stuck on, you cannot go further, you can even write me an email if you want. But I advise you to do it today, because tonight you will get a new sheet. Okay. About completely different subjects. But yet, as interesting. Okay?